So good morning. I'm going to present constitutive autonomy through motor-sensory self-programming. I am Olivier Georgeon from Lyon in France, and this work was done with Alexander Riegler from British University in Brussels. So I'm going to talk about constitutive autonomy, what it is, why should artificial agents have it, and how we can achieve it, how we can implement it in artificial agents. So that will be more the theoretical part of my talk. And then I will talk about design, how we designed it. So what we renounce if we wanted to, because there are some trade-offs here, we cannot address all problems. So what we renounce, we want to implement constitutive autonomy. I will talk again about the motor-sensory hypothesis that I introduced 2 days ago. The notion of self-programming, self-motivation will come in the way, and I will give some demonstrations. So constitutive autonomy. So it has received increasingly more attention recently. Here I quote this paper by David Vernon, 2015, which is one of the most recent. The paper is entitled Embodied Cognition and Circular Causality on the Role of Constitutive Autonomy in the Reciprocal Coupling of Perception and Action. And David Vernon makes the distinction between behavioral autonomy that focuses on the external characteristics of the agents, how it behaves, and constitutive autonomy that focuses on the internal organization and the organizational processes in the agents. So constitutive autonomy is the ability for the agent to develop and evolve its own international organization and organizational processes. Ezequiel Di Paolo, in an earlier paper, pointed out that the structural coupling between the entity and its environment should also evolve. So the entity should have the autonomy to evolve its coupling and interactional domain with its environment. So why is it important? Ezequiel Di Paolo, in this same paper, 2005, Autopoiesis Adaptivity Teleology Agency, insists on the importance of individuation of the agent. So if we design 2 robots that are initially the same, they have the same motors, same sensors, same initial software, we don't want them to do similar things. We want them to evolve individually based on their individual experience. So each robot will have different experiences interacting with the world, and we would like that after a time, they get their own personality, so to speak, or they become different one from the other. And it's an important feature if we want to be able to treat these robots as intelligent machines, because otherwise we will always consider that they just execute a predefined program, so there's no intelligence in that. Tom Froese and Tom Zimke in 2009 enacted artificial intelligence, investigating the systemic organization of life and mind, argued that constitutive autonomy is necessary for sense making. So sense making is the capacity to make sense of one's experience or interaction, what's going on. And so if we want to have a robot if we want to be able to believe that this robot makes sense of what is happening to it, it needs to have constitutive autonomy. It should not just process information in a predefined way, it should seem to incorporate this information and change itself based on this information. So our claim here, so we are based on the idea of computational entity. So a computational entity is an entity, so an object in the world, that has computational power. So it's maybe controlled by a computer. And we take computation is the very broad sense. Computation is just the capacity to change states into other states in a discrete, step-by-step way. So it's an intuitive sense of computation. So the constitutive autonomy of a computational entity, like a robot, amounts to learning new programs through their existence. That means we want this robot. So the robot physically may not evolve. It will always have the same sensors and same effectors and same motors. But its control system, its internal structure, so its program, we want it to evolve. So that means we want it to learn new program. So we are not the first to say that it should be possible. Vinograd said the internal structure of computer programs can change as the result of perturbation with the environment. Alexander Riegler, also earlier in 2002, argued that structural coupling with the environment is not necessarily limited to the physical domain. So even if we have always the same motors and sensors, we can imagine that the coupling between the algorithm that controls the robot and its environment can still evolve. So all that amounts, in more concrete terms, computational terms, all that amounts to acquiring new executable code as opposed to just acquiring data or parameters or weights or values or something. Here we want to acquire some code, that is something that can be re-executed by the robot. And of course, maybe it's not so difficult to record some code, but we want also that this code be executed in the appropriate situation. So we want that the learned code, to show that this learned code can be appropriately re-executed in the right situation, whatever that means. And we will see that this will involve the notion of self-motivation of the robot, because we want this code to be re-executed to satisfy the own robot's preferences or something. So we'll have to put some self-motivation in the robot. So again, the concept of self-modifying process is not new. Alan Newell, as early, and Herbert Simon, as early as 1976, mentioned it in their Turing Award lecture. John Wang talked about self-affecting cognitive architecture. Christine Torreson, more recently, has this paper on constructivist AI. But I've not seen any demonstration of of code that can be re-executed. Any demonstration where someone could say, oh, here, some self-programming has occurred. And that's what I am going to try to demonstrate today, although very modestly. So of course, self-programming raises many questions. So first, self-programming to do what? It's probably not going to program itself to become Microsoft Windows. So, so how do we define the preferences or the goals in the system that will somehow define what it will self-program, to what purpose it will self-program? So that relates to intrinsic motivation, and here will come some notions that we have been discussing earlier, the notion of impulse, predilection, chutzpah, I have learned from Peter 2 days ago, in which programming language? So it will probably not program itself in Python or in Java, but maybe we need to create a specific programming language that will be suitable for the agent to program itself. Should it create new instructions in this programming language, or is it enough if it reuses a predefined set of instructions? Should the execution engine evolve itself, or is it okay if the execution engine is pre-programmed? So we create this programming language, we create the execution engine, and all we want is just new programs in this predefined language with this predefined execution engine. So that's what we are doing so far. We are not studying how the execution engine will evolve. And then how to assess self-programming. Is this program that has been learned better than this other program that has been learned? This is a open question. Okay, so now I'm going to talk about a little bit of theory that will maybe provide some insight on how to do that. So we have been talking about Piaget yesterday. So there are two things we are interested in Piaget. So Piaget, in his famous book, The Construction of Reality in the Child, suggested that intelligence, the action of knowing, does not begin with knowing the self or the things as such, but with knowing their interaction. So he has a very strong commitment on focusing on interaction. So we are not going to predefine a model of the world or a model of the body of the agent, but we are going to predefine a model of the possibilities of interaction, an interactional domain. And then Piaget argued that intelligence organizes the world by organizing itself. So his whole book is about how the intelligence develops. So about constitutive autonomy, but of course, because that was before computer science, so he has ideas, but it's very difficult to translate them into computers. In his theory on genetic epistemology, he has this very important concept that is a sensory motor scheme. So a sensory motor scheme, in Piaget's sense, it's an atomic element. There is no distinction between sensor and motor. It's just the atomic element of cognition. And it makes sense when you think of, when you touch something, at the same time you move, and at the same time you feel. If you don't move, you don't feel. So they are really one element. It's an event of interaction in some sense. But of course, as computer scientists, we tend to separate input data and output data, so that raises a lot of questions. And then there is constructivist epistemology, which Paul mentioned yesterday. So it's not fancy rogue philosophy. It's really mainstream philosophy when you think of it. It's just the idea that the ontic nature of reality is not accessible. Here I quote Glasersfeld in his paper Radical Constructivism, but this idea has been here maybe for the last 200 years since Immanuel Kant. Maybe we don't have access to the state of the world as such. So in more cognitive computer science terms, we would say the states and transitions of the world are not accessible to the agent, and in fact they may not even exist. So the problem is how the agent creates the states or identifies the states and the transition before even being able to plan on reaching a particular state through particular conditions. So what we take from that is that we should not presuppose, that is, model a priori the states and transitions of the world. Because if we presuppose them, there is no way we can study how the agent can construct the state and construct the transition. So we should not give predefined labels to the agent, even if these labels are blank. So even if we don't give semantics to these labels, the mere fact of saying there is a state and there is a label, blank label on it, it's already a presupposition of what state and what transition exist. Okay, so from that, how do we design our agent? So what we renounce? So we renounce doing problem solving. We are not designing agents that reach a predefined goal state in a predefined domain, because we don't want a predefined domain, we don't want a predefined goal state. So we are not doing that, and we are lucky in a sense because we are not doing that, we are not exposed to the problem of complexity. Well, we are exposed to other problems of performance, etc. But there is no notion of complexity of a problem that we want to solve because we are not solving the problem. So we are not designing agents that get better in performing a predefined task. We want open-ended learning, no predefined task. We just want to show that some self-programming has occurred. We are not maximizing a scalar value, so we are not doing reinforcement learning, although we can use some reinforcement on some behavior, but it's not the traditional reinforcement learning in the sense that we seek to maximize a reward value. No. So we are not measuring the agent's performance through a scalar value. What I'm going to show is not a beautiful curve that goes up. Look, this reward value has increased. No, I'm going to show demos where we can argue that some self-programming has occurred. So those implementation of Piagetian and constructivist learning, some we have been made already. So Gary Drescher in '91 made a made-up mind, a constructivist approach to artificial intelligence. Howard Chaput in 2004, the constructivist learning architecture. Christine Torison in his paper 2012, a new constructivist AI from manual construction to self-constructive systems. So in particular, he says that the way any entity achieves grounding is through feedback loop. So there is again this importance of feedback loop as suggested by Piaget and other constructivist material. And of course there is Miller. But in all those implementations, I have not seen any demo in which we can see that some self-programming does function. So again, I'm talking about this motor-sensory approach. So as I said, usually as computer scientists, we decompose the sensory motor schemes as sensory, we receive data from the environment, and action. So here we propose another approach in which we consider that the motor is primary. So instead of talking of sensory motor loop, we talk on motor sensory loop, that is feedback loops, as opposed to perception action. In short, we don't consider the input data as a representation of the state of the world, because that would amount to providing predefined labels. So we consider input data as feedback from action. So as I said previously, with this in mind, we design different kind of machines. So it's more related to a control machine that tries to keep an homeostasis value than computation or processing machine that processes input data. And of course, it relates to Norbert Wiener's theory, but what we will put in that is constitutive autonomy on generation of intelligent behavior. And this has been, this theory of feedback loop has gained some attention recently. I think Andreas Lorenz has something in his previous presentation. Well, was also talking about feedback. I could quote also, Asada and Juntani in Japan who are interested in that. So really motor sensory cognition, the main idea is that we are not assuming that input data conveys a representation of the state of the world. So there are in fact less assumptions than in the perception action framework. So we do not predefine labels, so we are not cheating, in short. We are not giving labels to the agent as input data. The input data can be anything not representing the state of the world. And the good point with that is that it transfers nicely to robots. So when we do simulation in a simulated environment, we can very easily transfer our algorithm to a robot, because the robot in the real world, he does not receive label about the state of the world. So all we are doing, because our algorithm don't assume that input data represent the state of the world, then our algorithms transfer nicely to robots. And then in this framework, we consider perception not as input data, but as a construction, internal construction in the robot through sequences of interactions, through regularities of interaction. So there is no input data overload, because input data is feedback from action, so the robot controls the quantity of input data it receives. This is more argued in Alexander Rücker 2007. But we are not excluding unexpected input data. Sometimes a big noise can occur on that input data coming to us, even though we have not done nothing. We are not excluding that. Our model can include that, just feedback from doing nothing. And it has many technical advantages that I will describe. So basically what we are doing, we developed this algorithm based on events of interaction. So these are events of interaction, or sensory motor scheme. So in each of these symbols, there is action and feedback, action, feedback, action, feedback, action, feedback. We don't know what they mean, so we have no assumption of the semantics of those events. But we learn sequences, so it's very related to what Brett presented yesterday, we learned hierarchical sequences of events. So this sequence is represented by this higher level event on this by this, on this by this. And then at some point, we look if those higher level events, they match previously learned sequences. So here, this and this, they match this, so they will reactivate these sequences that we propose to continue. So this will be, oh, I have started that, I want to do that. This, I have started that, I want to do that. And then we have to make a choice. So those two subsequent course of action are proposed, but we need to make a choice. So here comes, how are we going to select? So different behaviors are afforded by the current situation. How are we going to select one particular? So here comes in self-motivation. We could implement different criteria to select one particular behavior instead of another. And depending on those criteria, we will have an agent that seems to have some particular motivation or other motivation. So for example, if there are some interaction that we say, oh, those interactions are bad, like hurting yourself. So you move or you bump on something that's bad. So we can put a negative value, and the selection mechanism will just don't want this interaction. But most interaction may be neutral. So we can have other criteria. For example, we can select something that we have not selected before in this context. So in this case, we have a robot that seems curious because it recognizes a context based on its previous interaction. It does something new in this context, so it's a curious robot. And here, the interesting thing here is that we just program impulses. We don't have, there is nothing that, it's not an answer to a need, it's not a goal that we want to reach, it's just this behavior, we select it because it seems nice in this context. And then when we have selected this abstract sequence, we execute the whole sequence that composes it. And that's where the self-programming comes in. We make the commitment of executing all this sequence, and we re-execute it in the appropriate situation. And that's where there is self-programming. And then on top of that, we can learn even higher levels. So we can have a recursive learning mechanism that increases works on top of knowledge. On this sequence, we are not obliged to execute them. We could simulate them internally, see how it goes, and that's where there is more even self-programming, because the agent can simulate them, create different simulations, and there is some self-programming. So this illustrates the coupling between the agent and the organ. So we have the box is the software that interacts with the world through input values and output values. And we define primitive schemes of interaction. So all those events of interaction, they are predefined. We create our robot, we design the motors, we design the sensors. So this is defined how this relates to how we created our robot. All those primitive events are predefined. There is a system that selects when scheme. So for example, in the sensory motor scheme, there is at the same time the action and the expectation of the feedback. So I want to touch, I move, and it's a control loop in which I feel at the same time. But of course, it depends not only on me, it depends on the environment. If I try to touch here, I will be engaged in a different control loop because there is nothing in the environment. So the scheme that I intend to enact will fail, and I will receive another scheme that is interacting with something else or with the void. So at each interaction cycle, we select an intended primitive scheme. We try to enact it, engage in this control loop, and we receive as feedback the actually enacted scheme. So maybe it was what I intended, maybe it was not. And from series of enacted schemes, we construct a representation of the situation. And then we learn a series of schemes. So there is this decision mechanism here that can select a higher level pattern, so that includes several primitive schemes. I want to enact this this higher level pattern, send it to the execution engine. It will control all the enaction of all over several interaction cycles, and then return what has been enacted, depending on the environment. And again here, the representation of the situation will be constructed based on what has been enacted and on what couldn't be enacted. So there is another coupling here, which we call the cognitive coupling, that can evolve as the agent learns new pattern of interaction, so new program. Okay, so demos. So we have this agent. It can move. So first demo is only in a grid cell, so it can move one cell forward, or turn left, or turn right, and it can smell those targets here. It's a distal sensory, you can think of it as smell. So this target doesn't move, but when the agent moves, it can smell the increase of smell. So at the beginning, it will just act randomly, but sometimes the smell increases, and we put positive value when the smell increases. So of course, it will have tendency to move forward this object. So here's the first demo. So at the beginning, it's just babbling. He doesn't know what it's doing. It's bumping into walls. But then after a while, he realizes that some action increased the smell. So it will just repeat this pattern, moving toward the target. But of course, it cannot know how far is the target. It can only know it's on the left, on the right, or in front, because it's only based on smell. So with the same algorithm, on the same, everything the same, just because the agent starts in another position and it has different individual experience, at the beginning it babbles, but it will learn another pattern. So in this case, it will learn to move one step too far until the smell decreases, and then move backward, and then align with the target, and move directly to the target. So here we see two different behaviors that we have not pre-coded. That's small sequences of interaction that are learned and reproduced in the appropriate context. And so yes, so that's our modest argumentation that there is some self-programming that occurs, and that makes some constitutive autonomy of the agent, because they all develop different behavior from that. So we have yeah. And it transfers nicely to robots. So it's exactly the same experiment. So we simulated the smell with a Kinect that detects those QR codes, but it's mostly the same principles. So it just learns those patterns of interaction to reach the target. So exactly the same algorithm, we just have to redefine the primitive schemes, how the primitive patterns of interaction are implemented, and then the algorithm is the same. But of course, it's much more difficult to see those different strategies that the agent learns, because it's more noisy. So here we create a new target. Okay, so I have another example. So in this example, we define 5 or 6 possible actions that the agent doesn't know what they mean. And for each action, we have 2 possible feedback. Again, the agent doesn't know what they mean. And we give some value in order to generate some interesting behavior. So there is, in fact, only one positive value, is this one. But so if it tries to do this action, if it's feedback white, it will get 5, but it's feedback red, it will get -10. So the algorithm will tend to try to enact this pattern of interaction, and to avoid this, and to do that, it will have to learn to use other patterns of interaction to put itself in the situation in which it can enact this pattern. And the demo is this. So again, the algorithm has no idea that it is controlling this agent in this environment. So some of these patterns mean feeling, so it can feel to the front, to the left, to the right, but again, it has no idea that it exists in a two-dimensional space. It has no idea what this means. It can turn left or right, move forward, or bump if there is a wall. So what it shows here is that it learns to use some sensory motor pattern of interaction as a perception, as active perception. So the agent learns to touch in front before moving forward, or not moving forward if there is a wall, and if there is a wall to touch on the left, on the right, and then turn in the right direction in order to just perform those interactions that we have defined as positive. So again, perception emerges as a result of behavior. It's not, perception is not predefined. So we can define different values for any possibilities of interaction. So of course, if we put a positive value for bumping into a wall, it will just learn to stay in front of a wall and keep bumping in it. Or if we define a positive value for turning, it will just spin in place and be happy with that. So the nice thing with that is that it's a way to implement primitive impulses or predilections that will show in the behavior of the agents. So just by analyzing the behavior, we can think, oh, so from this behavior, we infer some subjectivity to the agent. We can say the agent seems to like moving forward or dislike bumping into wall. And again, this transfers nicely with the robot. So the robot is similar. It can sense in front empty, sense to the right empty, sense to the left empty, sense in front a wall, sense to the left a wall, sense to the right a wall, turn left, turn right in predefined approximately 90 degrees, move forward, bump, and we just have to redefine how those patterns of interaction are implemented, and then it will work. The same algorithm will work. So we have the robot. The LED here shows when it activates its sensors. So front, front again. So we see the trace of activity. So it will be so front. So detecting the wall, but don't know what that means. So just picking random. So here moving forward, bumping. So here we can just infer that when we have detected the wall, then if we try to move forward, we bump. So we will just try to avoid that in the future. Of course, so with real robots, of course, it's noisy. Sometimes we have false detection or false positive, but the algorithm resists to that. And after a while, we can see that the robot has started to use its sensor in order to avoid bumping into walls. And so it's the same. Maybe I will go on, but so it works also in a dynamic environment. So here in this example, you should look at those two agents here that are sharks, and we have implemented the same algorithm that it is attracted by silent objects. So it has basic vision or smell or whatever you want to call it, and it will just explore any silent element of its environment, and then when it gets on it, it experiences some other kind of interaction. For example, it can eat the fish, it can bump into a wall, it can cuddle with the other shark, and very quickly it will learn some interesting behavior. So at the beginning they explore, they just bump into a wall, but explore different objects, explore so it works the same in a dynamic environment and continuous as opposed to grid work, because it's just feedback from action. So we implemented a positive value when they interact to each other, so they like to. So if nothing else, it helps us design agents that have a very natural behavior. So here, to implement that, we design a more complex cognitive architecture. So we still think in terms of events of interaction. So these little cubes here, or cylinders, they just represent events of interaction. So that's the timeline of events of interaction. And we have this hierarchical learning mechanism that learns, as I said before. But in addition to that, we have implemented an egocentric spatial memory where we can place the events of interaction in space. So the agent knows that this interaction is possible here, and this one is possible here. And the spatial memory is updated with the agent's own movement. So we simulated like the vestibular system that updates spatial memory when the agent moves. So it can detect some overlap of interaction. So if there is, through this sensory channel, I can make this interaction. On this other sensory channel, like seeing or touching, I can interact at the same place. Then I can infer that there is an object here that causes these possibilities of interaction. And from this inference, it can begin to construct a kind of phenomenal ontology, so an ontology of what objects are present here based on the possibilities of interaction that these objects afford. And then it's really not easy to find how we will propose behavior based at the same time from the sensory regularities and spatial regularities. So we're still studying how all this works. Probably we'll need more spatial memory. So here this is only an egocentric memory, but probably we'll need some hippocampal memory to have a memory like in the hippocampus to be able to simulate in an allocentric center of reference. And probably we need a whole cognitive architecture. So again, it transfers in robots. It's mostly the same experiment, but with a robot. And of course, it's very slow and noisy, but it works. So we simulate the fish here, and then we remove them. So it's supposed to have eaten the time. Okay, and I wanted to talk about internal simulation and the relation between impulses and goals. So what we implement with this mechanism is the impulse to react to an affordance. So the agent detects a possibility of interaction, and it has this mechanism that just activates the behavior that responds to this affordance. So it's more, so the internal motivation system is more like impulse than it's not trying to make any plan to reach a goal. So the idea is that impulse might be primary, but then how can we from that decide that we want to go to some places or make some more conscious plan to reach a predefined goal? So we try to illustrate that with this little experiment. So it's similar to previously. It can touch, bump. It cannot see, but it can touch, bump. And here it feels this thing, and we have put a very positive value for stepping on this floor here. So at some point, this is its temporal memory. This is its spatial memory. So it knows that those interactions has been made around it. And at some point, it can simulate patterns of interaction. So all that is in blue here is mental simulation of patterns of interaction. And from those mental simulation, it can find a way to go more efficiently to this flower that it likes. So in fact, this flower, at the beginning, it has only an impulse, and it just likes to step on it, and then after a while, it becomes a or choose goal if you wish, and it decides to go there, and because it's able to make plans to go there. Okay, so as a conclusion, so we are doing motor-sensory self-programming. That is, the agent learns programs that are series of motor-sensory schemes. That's the programming language that it used to learn this program. And the execution engine is, in fact, an emulator of the entity's body. So it stimulates its own action, and that's how it's self-programming. So it allows the evolution of the cognitive coupling between what we call the cognitive part and the executive part. So in a sense, the cognitive part sees the world in increasingly more sophisticated possibilities of interaction. As the entity develops, the cognitive part sees, that's what I said. So we believe that it's an approach, a modest starting point for addressing the question of open-ended learning driven by intrinsic motivation. And that's it. Thank you for your attention.
Any questions?
Any questions? Olivier, I was interested in your mental simulation stuff that you presented here at the end. How much far in the future you are being able to do in this internal simulation? Because it's just for the immediate satisfaction of the goal, or you can think, for example, if you have a second agent in the field, that they could be competing for some goal, and so I could anticipate the other is going to reach the goal before me, or things like that.
So currently not that far.
Okay.
The question, it's an important question, the existence of other agents. So of course, just to understand that other agents exist, you have to be able to recognize so you have to interact with other agents, find out. So you have to construct this so in this ontology here, you have to find out that there is some entities that exist that behave as other agents, so they are not just behaving as passive elements, but as other agents. And interestingly, in fact, you also have to construct your own ontology, the ontology of the own entity, and somehow there is some possibility that the agent realizes that those two entities are similar, myself and the other agents, and then maybe I can project some behavior on the other, and then we could go on that way, but we don't know how to do that.
And do you use any specific algorithm for doing this planning, or you're just doing it from scratch?
From scratch.
Hi there, it was very good. I had a question about one of the early slides, which had cognitive coupling and I think behavioral coupling.
Yeah.
Can you go back to that one?
Yeah.
Thank you.
Yeah, this one.
Yep. Yeah, that's the one. Yeah, primitive coupling.
Yeah.
Could you say that is sort of a parallel to the dual processing theory, where you have a system 1, system 2 kind of concept there? Would you say those layers are similar to system 1 and system 2?
No, not really. Because so at the beginning there is only the primitive coupling. So at the beginning we define the primitive schemes of interaction, and the decisional mechanism is here really. So it can only decide what primitive schemes I can enact. But then after a while it learns composite patterns, if you wish, so sequences of patterns. So in some sense the cognitive coupling over time rises up. So it's not predefined. It's because it will increasingly, it will learn increasingly more longer patterns and longer schemes. So over time, it will it will raise up. So it's not predefined. It evolves.
Okay. And then later on, you were talking about simulation.
Yes.
Would the simulation be done there in the coupling?
Yeah. So probably the simulation. So yeah, we could imagine two solutions basically. We could say, oh, we are going just to inhibit output values. So we are going to run that and I don't know, try to implement here. So the simulation goes in spatial memory, basically. So we have a spatial memory. So in fact, it's on this diagram, it's not very clear what it can be, but so maybe it's probably the decision mechanism here has its own architecture. So the architecture is in the decision mechanism. It has spatial memory, and it will simulate. So somehow what the controller enacts will send to spatial memory instead of sending to the output world.
Thank you. Anybody else?
How do you see the higher levels connected?
Depends
So
on what you mean by higher level.
Language, for instance.
So what we foresee, so the like abstract reasoning.
Yeah, or language.
Yeah. So we follow this hypothesis that abstract reasoning reuse basic spatial capacity of the brain. So the brain has this capacity to navigate in space, find its way in space, and there are those theories that say when you reason at an abstract level, you reuse those capacity to simulate pathway in space. So that's how we see it. So we think that only by implementing the right spatial memory, probably we need different patterns of spatial memory. We need egocentric memory, allocentric memory, any kind of spatial that we need to interact with each other. And if those hypotheses are right, just by having this in the architecture, at some point it should be able to use this to create higher level reasoning. But you know.
Yeah, that sounds great. Wonderful experiments.
Were there any other questions? Okay. Great, thank you.